Hey guys, my name is IBM, and today I gathered the courage to record some lessons for my students, and therefore I would like to share them again with anyone on YouTube. So this is physics with IBM, and this is the Cambridge International Education Curriculum, and this is going to be, or this is A-Level Physics 9702. Which is actually paper 4. Just to remind you of the course outline for those of you who are doing paper 4. The course outline involves concepts such as circular motion, which I have already recorded, concepts like gravitation, which I will record later on, concepts like ideal gases, which I have already recorded, concepts like temperature, which I'm going to record today, concepts like thermodynamics, which I've already recorded, concepts like simple harmonic motion, which I've already recorded, oscillations already recorded, electric fields I'll record it later, magnetic fields and electromagnetic induction I'll record it later, capacitancy, that one has already been recorded, alternating current has been recorded, nuclear physics has been recorded, quantum physics will be recorded later on. Astrophysics and cosmology has already been recorded, and finally medical physics, that will be recorded later on. So these are the topics which make up A-Level Physics paper 4, and they are quite many and they are quite broad, but if you master the concepts under each topic, you can always get an A in this paper. So let's very first go to temperature, because we are currently going to deal with the temperature as the last part of thermal properties. So let's go to temperature. So the general topic, which has these three units, is normally called the thermal properties, which comprise of ideal gases, that has been already recorded, temperature, which I'm recording, and thermodynamics, which has already been recorded. So let's go to temperature in more details. So it's supposed to be 3.2. In your syllabus, you can always verify. So under temperature, we shall explore concepts to do with thermal equilibrium. We shall talk about temperature scales. We shall talk about specific heat capacities and latent heat capacities. And I think that will be the end of this area, or this chapter, or this unit called temperature. So this is going to be lesson 1 of temperature. So let's go straight away to the first concept, which is thermal equilibrium. So what do we mean by thermal equilibrium? At least from other topics, we know the meaning of the term equilibrium. We know what equilibrium means. But this time, I want us to be specific and talk about thermal equilibrium. So our everyday idea of temperature is based on our sense of touch. For example, putting your hand into a cup containing ice immediately gives a sense of cold, and putting the other hand into a cup of warm water gives the sense of something that is hot. So we therefore say that the water is at a higher temperature than the ice. And let's assume that one end of a metal bar is heated by say pouring water over it. And the other end is cooled, or the other end is cooled by holding it under cold water or under a cold water tap. So the effect of the temperature difference between the ends is that thermal energy is actually going to be transferred or thermal energy is going to be transferred along the bar from the region or the point at high temperature to the point where there is actually low temperature. So when two bodies at different temperatures are in contact, thermal energy is transferred from a region of high temperature to a region of low temperature, that is, from the hotter to the cooler, until what we call thermal equilibrium is established. So I said you have, for example, let's say a metal rod. One end of the metal rod is placed on a burning flame, for example. Let's say this is a flame, and the other end is maybe placed under a tap of running water. So this is going to be hot, therefore the other end is going to be cold. So there's a difference in temperature between the left-hand side and the right-hand side. So we expect that naturally heat is going to flow from the hot end to the other end, and heat will only stop flowing if this cold end also is at the same temperature as the hot end. At that point, we say thermal equilibrium has been established. And when thermal equilibrium is established, it means the hot end and the cold end must now be at the same temperature. So if we turn off, say, the tap, then it means, let's say this was at 20 degrees Celsius and the other side was at a temperature lower than 20 degrees Celsius. So heat is going to flow from this hot end to the other end until a point where the other end is also at the same temperature, let's say 20 degrees Celsius. At that point, when the temperature is the same, we say that thermal equilibrium has been established. So for thermal equilibrium, you have to be talking about same temperature. And when the temperature is the same, then we cannot say that heat is flowing from the hot region to the colder region because the temperature on both ends of the object is the same. In that case, therefore, we say that there is no net flow. There is no net flow of thermal energy in any particular direction. In other words, energy flows or thermal energy flows equally in all directions, so that there is no net flow of thermal energy in any particular direction. And that's what we are going to call, or that's what we call, thermal equilibrium. So heat naturally flows from a region of high temperature to a region of low temperature as long as there is a difference in temperature between the two ends. But if there is no difference in temperature between the two ends, then heat flows equally in all directions. So we saw that there is no net flow of thermal energy because the temperature is the same. So we say thermal equilibrium has been established. So what we are saying is very simple, that when different regions or bodies in thermal contact are at the same temperature, they are said to be in thermal equilibrium. And whenever there is thermal equilibrium, there is no net thermal energy flow in any particular direction. There is no net thermal energy flow in any particular direction. I want you to note that it would be wrong for you to say that there is no transfer of thermal energy between the two ends or the 2 points here. Even if this is at 20 degrees Celsius and the other one has also now become 20 degrees Celsius, we can't say there is no transfer of thermal energy between the two ends. There is still transfer of thermal energy, but there is no net transfer. No net transfer. There is no resultant flow of thermal energy in any particular direction because energy or thermal energy is now flowing in all directions equally, so that there is no resultant flow in any particular direction. So this is not the same case when there is a difference in temperature, because whenever there is a difference in temperature, heat naturally flows from a region of high temperature to a region of low temperature. And that is very, very important. So what do we mean by thermal equilibrium? So whenever thermal equilibrium is established, the bodies or two regions or two ends in thermal contact are at the same temperature and there is no net thermal energy flow in any particular direction. That's what we mean by thermal equilibrium being established, or that's what we basically mean by thermal equilibrium. Whenever there is no difference in temperature, there is no net flow of thermal energy in any particular direction, then we say thermal equilibrium has been established. The hotter body normally loses internal energy while the cooler body gains internal energy. And I have said that the thermal equilibrium is a dynamic situation where the transfer of heat energy between two objects or two regions is actively going on in both directions but at the same rate. So it would be wrong for you to say that there is no transfer of thermal energy between them, although you would say that there is no net thermal energy transfer, unlike that between objects at different temperatures. So that's what we mean by thermal equilibrium. Bodies in thermal contact are at the same temperature and there will be no net thermal energy flow in any particular direction. And that's what we mean by thermal equilibrium. Okay, let's now talk about temperature scales, because So temperature needs to be understood as a scale of hotness, indicating the direction of flow of energy, and heat can transfer between places at different temperatures. We know that heat is a form of energy, but temperature is the average kinetic energy of the molecules that make up the system or that makes up matter, as we saw in thermodynamics. So temperature tells us the degree of hotness. Temperature tells us the degree of hotness or coldness of a body with respect to some standard, which standard is normally given by what we call a thermometer. And on a thermometer, we have what we call a temperature scale. Although the temperature does not tell us does not measure the amount of heat energy, it just tells us the degree of hotness or coldness of a body with respect to some standard. And that standard is what we want to establish now, which is normally found on what we call a thermometer, and that's what we call a temperature scale. So to establish a temperature or thermometer scale, we have to consider two things. And which things do we consider? Of course, the various degrees of hotness are represented by a temperature scale, and in order to establish it, we have to consider two major things. The first one is what we call a thermometric property. Of course, a thermometric property is a physical property which varies, or it is actually considered to vary, or it is always assumed to vary or to change linearly with the temperature. So we must consider a thermometric property, which is a physical property which is assumed to vary or to change linearly with the temperature. That's what we call the thermometric property. So if we know the thermometric property, then we are about to establish what we call a temperature scale, or a standard on which measurements of temperature can be obtained. Number two, we also need to have what we call fixed points. So we need two fixed points. The fixed points are 2 degrees of hotness which are easily and accurately reproducible. In your IGCSE, you must have mentioned two fixed points, for example, the ice point and the steam point. These ones are degrees of hotness which are easily and accurately reproducible in several experiments. So if I have the thermometric property and I have two fixed points, then I can easily establish what we call a temperature scale or a thermometric scale or a thermometer scale. What are these thermometric properties that we normally consider when establishing a temperature scale? So examples of thermometric properties, we have the volume of a liquid or the length of a liquid column. Most of the liquid in glass thermometers use this thermometric property that when you place a thermometer in a boiling liquid, the liquid column, which is mercury inside the thermometer, rises, which means the length of the liquid column rises because the mercury is expanding, its volume is increasing. So the volume of a liquid or the length of a liquid column changes with the temperature. So we call it a thermometric property because thermometric property is a physical property which varies or is assumed to vary linearly with the temperature. Number two, we have what we call the resistance of a wire or a thermistor. Of course, we know that for a thermistor, the resistance of a wire decreases when temperature increases. That is what we call a negative coefficient thermistor. So because the temperature is causing the resistance to change, it means the resistance is a thermometric property because it varies with the temperature. Number three, we have what we call the EMF of a thermocouple. The EMF of a thermocouple, or the so-called thermoelectric EMF, changes as the temperature difference between the two junctions of a thermocouple changes. So that one can also be used the EMF of a thermocouple can also be used as a thermometric property. We also have the pressure of a fixed mass of a gas at constant volume. We know that the pressure is directly proportional to temperature if the volume is constant. So the pressure of a fixed mass of a gas at a constant volume is also going to act as a thermometric property because it will vary linearly with the temperature. We also have what we call the color of an electrically heated wire. When a wire is heated electrically, it starts changing colors. Of course, different colors correspond to different temperatures according to Wien's displacement law that you might have seen in cosmology and astrophysics. So We know that wavelength is inversely proportional to the absolute temperature according to Wein's displacement law. And of course, different colors correspond to different temperatures. So it means the color of an electrically heated wire changes as the temperature changes. So we can use the color of an electrically heated wire as a thermometric property. So these ones are physical properties. We call them physical because we can easily observe them. They are physical properties which vary linearly with the temperature. Then let's talk about also the fixed points, examples of fixed points. Like I mentioned in IGCS, you mentioned two fixed points. You mentioned two fixed points in IGCSE, and you mentioned the ice point. Remember, I said these are 2 degrees of hotness which can easily be reproduced. So in IGCS, you mentioned the ice point, and this is the temperature of pure melting ice. And in IGCSE, you assigned this a value of 0 degrees Celsius. So 0 degrees Celsius is what we call the ice point. You also mentioned the steam point, the steam point. So the steam point, which is actually the temperature of the steam from pure boiling water. The water should not be having impurities. And the steam point is considered to be 100 degrees Celsius. That is the temperature of steam coming from pure boiling water. So these two fixed points that you mentioned were helping you to establish what you call the centigrade scale. You were establishing what is called the centigrade scale of temperature, or the centigrade temperature scale, or the Celsius scale. So how do we use these two fixed points to come up with a Celsius scale or the centigrade scale? So we have talked about the ice point as being 0 degrees Celsius. We have talked about the steam point as being 100 degrees Celsius. And we say these are two fixed points. So by taking the value of the thermometric property at the two fixed points and dividing the range of the values into a number of equal steps or equal degrees, we can set up what we call an empirical scale. Empirical. We set up what we call an empirical scale. We set up what we call an empirical scale of temperature for that thermometer. Of course, the word empirical means derived by experiment. And if we choose to have 100 divisions between 0 and 100 degrees Celsius, if we choose to have 100 equal degrees or 100 equal divisions between 0 and 100 degrees Celsius, between the temperatures correspond to these fixed points, taken as 0 degrees and 100 degrees respectively, we arrive at what we call the empirical centigrade scale of temperature for that thermometer. So it is called empirical because it is going to be derived from an experiment. That is, we are going to measure the thermometric property at ice point. We shall measure the thermometric property at steam point. And then we divide the range between 0 degrees Celsius to 100 degrees Celsius into 100 equal divisions to come up with what we call the centigrade scale or the empirical centigrade scale. Of course, there is nothing special about these two fixed points. In fact, for the centigrade scale, these two fixed points can even change. Even though we call them fixed points, these two fixed points change. They both change if the pressure changes, or if the ice is not pure, or if the water is not pure. The fixed point may not be the two fixed points may not be 100 degrees Celsius and 0 degrees Celsius if the water is not pure, if the ice is not pure. So there is nothing special about these two fixed points. So to establish the centigrade scale, we have to measure the thermometric property. Let's say X is the property which varies linearly with temperature. So we measure the thermometric property or the value of the chosen thermometric property at ice point, that is at 0 degrees Celsius. So I'm calling it X naught or X0. Then I would measure the value of thermometric property chosen at the steam point, and I'm calling it X100 because steam point is 100 degrees Celsius. Then we can now measure the value of the chosen thermometric property at the unknown temperature. So let's say the unknown temperature is theta. So the value of the property of thermometric property is x theta. So we measure x theta at the unknown temperature theta. And of course, it means from the centigrade scale, we can easily find theta, because we can use x100 and x0 to draw what we call a calibration curve, which we can use to determine any unknown temperature. For example, I measure the property, let's say the property is length of a liquid column. So I measure the length at ice point, that is at 0 degrees Celsius. Then I measure the length at steam point, that is 100 degrees Celsius. And then I measure the length at the unknown temperature, which is x theta. So how do I arrive at this expression here? Theta in degrees Celsius being called x theta over x100 minus x theta, I mean x naught, x theta minus x naught over x100 minus x naught times 100, where this is the expression I could use to find the temperature, the unknown temperature on the centigrade scale. So because the property varies linearly with the temperature, and it is a straight line, then I can employ the gradient to find this expression here. So I'll show you how to arrive at that expression, even though it's not necessary to derive it. I'll just show you how to arrive at it. So using gradient, I'll say x 100 minus x naught divided by 100 minus 0. That is gradient. Using another pair of points on the same straight line, I'll have that x theta minus x naught divided by divided by theta minus 0. So when I make theta the subject, I'll have that theta into x 100 minus x naught is equal to x theta minus x naught times 100. I just cross multiplied. So when I divide, I have that theta is going to be equal to x theta minus x naught divided by x 100 minus x naught, and this is multiplied by 100. So we arrive at that expression for determining the unknown temperature on the centigrade scale. So it is equivalent to dividing the range between 100 degrees Celsius and 0 degrees Celsius into 100 equal divisions, and that's what we call the centigrade. That's what we call the centigrade scale of temperature, and it is the most common scale of temperature that we use almost on a daily basis. So I want us to note that the choice of a different thermometric substance and thermometric properties would lead to a different centigrade scale. Imagine you are using two thermometers. One uses mercury in them, another one uses alcohol. These two thermometric substances do not behave the same way with the temperature. So because they don't behave the same way with the temperature, they may agree at the fixed points, but they may not agree at points in between the fixed points. So the choice of different thermometric substances and the thermometric properties would lead to a different centigrade scale. Agreement between scales only occurs at fixed points. So two thermometers, one using mercury, another one using alcohol, may measure room temperature, and one gives, let's say, 23 degrees Celsius, and another one gives 23 or 24 degrees Celsius for the same room. And why are they not agreeing at the room temperature? It's because the thermometric properties, we assume that they vary linearly with the temperature, but they not perfectly vary linearly with the temperature. That's number one. These thermometric substances may not actually behave the same way. So that is a disadvantage of the centigrade scale. It depends on the thermometric substance and thermometric property being chosen. Yet these properties may not perfectly vary linearly with the temperature. So this happens because the thermometric properties may not vary perfectly linearly with the temperature, as they are always assumed to. The thermometric properties may not vary perfectly linearly with the temperature, as they are always assumed to. It is also found that the difference between the empirical scales or the experimental scales are smaller in the case of thermometers based on gases as thermometric substances. So instead of using liquids such as mercury or gas or alcohol, experiments have shown that if the thermometers use gas, then the difference in the scales or the disagreements in the thermometer in the temperatures measured becomes even smaller. So it is found that the difference between the empirical scales are much smaller in the case of thermometers based on gas as thermometric substances. For example, we have the constant volume gas thermometers, which I will talk about later on. But for thermometers relying on liquids, for example, two thermometers may not agree on the same measurement because the thermometric properties may not perfectly vary linearly with the temperature as they are always assumed. But for gases, if gases are ideal, it is believed that for unideal gas, we mentioned in thermodynamics or in ideal gases that PV equals to nRT. So for unideal gas, at a constant volume, pressure varies perfectly linear with the temperature. So if the thermometer uses a gas as the thermometric substance, the pressure of the gas varies perfectly linear with the temperature. And if the gas is ideal, then the relationship is going to be perfectly linear. That means for whatever gas, as long as it is ideal, two thermometers using different gases, which gases are ideal, are going to completely agree on a measurement. Okay, example, the value of our resistance in a piece of wire is 3 ohms at the ice point and 8 ohms at the steam point. What is the temperature of the wire if its resistance is 5 ohms? So one, we are going to assume that the resistance is the thermometric property, and we are going to assume that the resistance varies linearly with the temperature. So if it varies linearly with the temperature, then I will sketch a graph. I will sketch a graph which I expect it to be a straight line. So I will say this is resistance against temperature. So let's say this is the resistance in a piece of wire is 3 ohms at the ice point. So let's say at 0 degrees Celsius. At 0 degrees Celsius, the resistance is 3 ohms. And let's say they say that steam point it is 8 ohms. So steam point is 100 degrees Celsius. So at 100 degrees Celsius, the resistance is at 100 degrees Celsius, the resistance is 8 ohms. And then 5 ohms is between 3 and 8. So I will put 5 ohms here. So 5 ohms is between 3 and 8. So 5 ohms, let's say the temperature is theta. So the question is, what is the temperature of the wire if its resistance is 5 ohms? So using the graph, just using gradients, because this is a calibration curve. So using gradients, I will say 8 minus 3 divided by 100 minus 0 is going to be equal to 5 minus 3 divided by theta minus 0. So this is going to give me 5 divided by 100 equaling to 2 divided by theta. When you cross multiply, you have theta times 5 equaling to 2 times 100. Then you divide by 5 on both sides. So theta is going to be equal to I think this is 40. I think this is 40 degrees Celsius. Okay, so theta is going to be 40 degrees Celsius. So you don't need to cram the formula that we derived. You just assume that the variation is linear, and therefore if the variation is linear, it implies that the calibration graph will be a straight line, which would give you such an answer without even remembering the expression or without remembering the formula. Okay, example number 2. If the length of a Maclay column in Maclay in glass thermometer is 25 millimeters at ice point and 180 millimeters at the steam point, what is the temperature when the length of the column is 55 millimeters? So again, we are going to assume that the length of the liquid column varies perfectly linearly with the temperature. So we are seeing at 0 degrees Celsius, it is lower than at at steam point. So it is increasing. So it is going to be a straight line. So let's say this is 0 degrees Celsius. This is 100 degrees Celsius. So at steam point, which is 0 degrees Celsius, the length is 25 millimeters. And at 100 degrees Celsius, which is at steam point, the length is 180 millimeters. That is at steam point, which is 100 degrees Celsius. What is the temperature when the length of the column is 55? So we know that 55 is between 25 and 180, so I'll estimate to be somewhere here. So this is 55 millimeters, and we want to find the temperature. So I'll just use the gradient. So I'll say 180 minus 25 divided by 100 minus 0. This is the same as 55 minus 25 divided by theta minus 0. So 180 minus 25, I think that is 155 divided by 100 should be equal to 55 minus 25, which is 30, divided by theta. Then we cross multiply. So theta is going to be equal to 30 times 100 divided by 155. So theta is 100 times 30 divided by 155, which is 19.4. So theta is going to be equal to 19.4 degrees Celsius. Okay, so that's going to be our temperature when the length of the liquid column is 55 millimeters. And you notice that 19.4 is between 0 and 100 degrees Celsius because 55 was between 25 and 180 millimeters. A resistance thermometer has resistance 95.2 ohms at the ice point and 138.6 ohms at the steam point. What resistance would be obtained at a temperature of 19.4 degrees Celsius on the centigrade scale of this resistance thermometer? So we are seeing it is a resistance thermometer and it has 95.2 at ice point, 138.6 at the steam point. That means the temperature increases with, the resistance increases with the temperature. So I'll sketch the graph again for guidance. This is the calibration graph. So assuming the variation is linear, so this is going to be at 0 degrees Celsius. Let's say this is at 100 degrees Celsius. This is temperature against resistance. So at steam point, the resistance is 95.2 ohms, and that is at ice point. Then at steam point, the resistance is 138.6 ohms. And we want to find the resistance when the temperature is 19.4. So 19.4 is between here. I can just estimate. So let's say this is 19.4 degrees Celsius. So for 19.4, we want to find the resistance. I'll just call it R. So I would just use a gradient. So I'll say 138.6 ohms minus 95.2 ohms divided by 100 minus 0 should be the same as R minus 95.2 divided by the temperature is 19.4 minus 0. So I'm just going to cross multiply. Let me first subtract and simplify. So I have 138.6 minus 95.2. So that is 43.4 divided by 100 equals to R minus 95.2 divided by 19.4. So when I cross multiply and make R the subject, R is going to be equal to 43.4 divided by 100 times 19.4, then plus 95.2. So 43.4 times 19.4 divided by 100 plus 95.2. So this gives us R as 103.6 ohms. So the resistance is 103.6 ohms. Okay. So here is a self-check. Here is a self-check, which I expect my students to always try out, but I will give a hint because I know my students may be able to solve the self-check, but not all the students would be able to solve the self-check. The EMF of a certain thermocouple is 5.6 millivolts when one junction is placed in melting ice and the other in steam. So let me just sketch a thermocouple here. So this is the voltmeter where we have one junction here, another junction the other side. So let's say this is in ice and the other one is in steam. So this is in 0 degrees Celsius, the other one is 100 degrees Celsius, and the reading here is 5.60 millivolts, which means that X theta, which is EMF 100 minus EMF of 0 must be equal to 5.6 millivolts. With one junction in melting ice and the other in a boiling liquid, the EMF is 22.46. That means now EMF in the unknown temperature minus EMF in melting ice, the difference, this corresponds to 2.46 millivolts. Then calculate the boiling point of the liquid on the centigrade scale. So EMF 100 minus E naught 0, this is divided by 100 minus 0 is the same as E theta minus E naught divided by theta minus 0. So this is going to be 5.6 millivolts divided by 100 equaling to 2.46 millivolts divided by theta. So just make theta the subject and theta will be equal to, theta is going to be 2.46 times 100 divided by 5.6. 2.46 divided by 5.6 times 100. So this gives us theta as being equal to 43.9 degrees Celsius. So I have already solved that. The gain of an electric circuit is found to depend on temperature. At 5 degrees Celsius, the gain is 110, and at 18 degrees Celsius, it is 125. Assume that the gain depends linearly on Celsius temperature. Estimate the gain when the circuit is used on a hot day at a temperature of 25 degrees Celsius. So you notice that at 5 degrees Celsius, the gain is 110. At 18 degrees Celsius, the gain is bigger. That means the gain increases with the temperature. And we notice that 25 degrees Celsius is above 18. So I can still use a calibration graph to find that. So I'll just erase this because I don't have any other space. So using the calibration graph, I'll use the calibration graph here. So let's say this is temperature and this is going to be the gain. And it is actually going to vary linearly with temperature. So let's say at 5 degrees Celsius, the gain is 110. Then at 18 degrees Celsius, the gain is 125. Then at 25 degrees Celsius, because 25 is higher, so I'll put 25 here, 25 degrees Celsius, so the gain should be higher. Let me just call it G as the gain. So if the variation is linear, then I'll just use a gradient. So I'll say gain G minus 110 divided by 25 minus 5 is going to be equal to 125 minus 110 divided by 18 minus 5. I'm just using gradient. The gradients are equal for whatever pair of points that you take. So the gain is going to be equal to, let me simplify this, 125 minus 110, which is 15, divided by 18 minus 5, which is 13, times 20, then plus 110. So we have 15 times 20 divided by 13, then plus 110. So this gives us a gain of 133. It is 133. To three significant figures is 133. So that would be the gain. Okay, on the centigrade scale. Then lastly, the resistance of a thermistor is 3500 ohms at 2.0 degrees Celsius. At 20 degrees Celsius, its resistance is 1800. So we see that this is a decrease. So even if the resistance varies linearly with the temperature, as temperature increases, it's like the resistance is decreasing. So the graph will be a straight line, but not going upwards, to be going downwards. The thermistor is used as a thermometer. What will be the recorded temperature when the thermistor is 2150 ohms if the resistance of the thermistor is assumed to vary linearly with the temperature? Suggest why the temperature are measured using a Maclean glass thermometer may give a different value for the temperature. Okay, so starting with the last part, why the temperature measured using a Maclean glass thermometer may give a different value of temperature. In the first place, uh, the variation of resistance of a thermistor with the temperature is not the same as the variation of length of a liquid column in a Maclean glass with the temperature. In fact, they don't vary perfectly linearly. In fact, the variation of the resistance of a thermistor with the temperature is not linear at all. We just assume it is linear, but it's actually going to be, if you recall from your electricity, the graph of resistance against temperature for a thermistor was a curve like this. But here they are saying it is assumed to vary linearly, so they are approximating it to be linear. That's number one. Number two, the variation for a liquid in a glass thermometer, temperature is directly proportional to the length of the liquid column. Yet for a Maclean glass, yet for a thermistor, temperature is inversely increase in temperature leads to a decrease in resistance. So temperature is inversely proportional to the resistance of a thermistor. So they are not varying in the same way, and they are not varying, and the resistance of a thermistor does not vary linearly with the temperature. Okay, so I'll just use the same space for the calculation. I'll begin with the calibration curve because they have assumed it is linear, yet it is always not linear, so it is going to be a graph like this. So this is our resistance against temperature. So they have told us at 2 degrees Celsius, the resistance is 3500. Then at 20 degrees Celsius, the resistance is 1800. Now we want to find 215. Okay, let me try to expand this. So let's put 20 here, and the resistance corresponding to 20 is 1800. Then the other one is, we know 2150 is between these two, so 2150 is between these two, and this temperature is going to be theta. So using a gradient, again it is a straight line, so I'll say gradient. If I start with the 3500 minus 1800 divide by the temperature. I started with 3500, so this is going to be 2 minus 20. This should be equal to, again I'm starting with the 2150 minus 1800. The corresponding temperatures for 215 it is theta, and for 1800 is 20. So I have to simplify this. So 3500 minus 1800, so this is 1700 divided by negative 18 equals to 2150 minus 1800. This is 350 divided by theta minus 20. So we just cross multiply. So theta minus 20 equals to negative 18 times 350 divided by 1700. So we take the minus 20 the other side, it becomes plus. So theta is going to be equal to minus 18 times 350 divided by 1700. So this is minus 3.7 plus 20. Yes, minus 3.7 plus 20. That means theta is going to be equal to theta is going to be equal to 16.3 degrees. So theta is 16.3 degrees. Explain why two thermometers using centigrade scale may give different values of room temperature when used at the same time. It is similar to the question I've just answered here. So two thermometers using centigrade scale may give different values of temperature because it depends on thermometric substance and thermometric properties, yet the thermometric properties may not vary linearly with the temperature as they are always assumed. And different substances, of course, behave differently or respond differently to temperature. Okay, so that is for the centigrade scale. So we said, or we mentioned that for thermometers, or experiments have shown that thermometers which use gas give a smaller difference in their measurements. In fact, the difference in the centigrade scales of thermometers using gas is very, very small. And a good example is the thermometers which are relying on, which are, the constant volume gas thermometer, where in this kind of thermometer, we can make the pressure of the gas to vary linearly with the temperature. So for a constant volume gas thermometer, the thermometric property can be the pressure of the gas, where we can still measure, or we can still measure the pressure of the gas at steam point. We just put the gas at steam point. That is, we find the temperature of the gas at steam point. The pressure of the gas at steam point, which steam point is 100 degrees Celsius. And we measure the pressure of the gas at 0 degrees Celsius. And we now plot a graph. Of course, because this thermometer is using gas, where for a gas, pressure or PV is equal to nRT. If the gas is ideal, then at constant volume, the pressure is perfectly varying linearly with the temperature, which would give us a perfect straight line like this one here. So for a constant volume gas thermometer, the property is considered to vary perfectly linear with the temperature. That is, if the gas is ideal, the variation is extremely perfect. The extrapolated temperature is found to be minus 273 degrees on the empirical centigrade scale. So just to slightly take you back here, when a graph of pressure, which is the property against temperature, is sketched for a constant volume gas thermometer, we notice that the pressure cannot be zero at 0 degrees Celsius. In our attempt to try to find the temperature for which the pressure becomes zero, we extrapolate the graph backwards, and experiments have shown that the graph cuts the x-axis at a value which is close to around minus 273 degrees Celsius. If the experiment is repeated with a gas at even lower pressures, it is found that the extrapolated temperature goes to negative 273.15 degrees Celsius. So scientists believe that this is the smallest possible temperature that we can reach, even though experimentally we have never reached it. They believe that this is the smallest possible temperature in real life. And this temperature will later on be used to establish what we call the absolute scale of temperature, or the thermodynamic scale. Okay. So taking the graph backwards, or the extrapolated temperature is found to be minus 273 degrees on the empirical centigrade scale. If the experiment is repeated with the lower and lower pressures of gas in the thermometer, the extrapolated temperature tends to a value of minus 273.15 degrees Celsius. This temperature is what is known as absolute zero on what we call the thermodynamic scale, or the absolute scale of temperature. So this value has a big significance, as we are going to see, and it is not going to depend on any particular substance. It is not going to depend on any particular substance, because we have seen how we arrived at it. For thermometers which use gas, the deviation in their measurements is very small. We saw that when a graph of pressure against temperature is plotted for a thermometer using gas, we notice that if the gas is ideal, pressure varies perfectly linear with the temperature. In our attempt to try and find the temperature for which the pressure becomes zero completely, we notice that the graph cuts the x-axis at around minus 273.15 degrees Celsius. And we believe that this is the smallest possible temperature, and we call it the absolute value or the absolute zero on the thermodynamic scale. And it is going to be just a theoretical value, because in practice it has never been reached, or it cannot easily be reached. So it is called absolute zero because it does not depend on the thermometric properties of any substance. So it is not depending on any thermometric property of any substance. That's why it is called absolute. It is actually absolute. So this leads us to what we call the absolute scale of temperature, or the thermodynamic temperature. So just like the centigrade scale, we also need a fixed points. Unfortunately, we don't need a thermometric property here. We just need a fixed points because the absolute scale will not depend on the thermodynamic. I mean, the absolute scale will not depend on the thermometric property of the substance because its fixed points are very more significant compared to the fixed points on the centigrade scale, which do not depend on any thermometric substance. So this absolute scale, called the Kelvin scale, called the thermodynamic scale, is different from other scales because we set it up without using any particular property of any particular substance. It is not set up using a particular property of a particular substance. And this is better. It is a better scale in that one of its fixed points, which we have already mentioned as the absolute zero, has a greater significance than either of the centigrade fixed points. It has a greater significance than the zero, the ice point. It has a greater significance than the fixed point. I mean, than the steam point, because for it does not change irrespective of where, because it is not depending on the properties of the substance, whether the substance is pure or impure, it does not change. But for fixed points such as the ice point and the steam point, we saw that there was nothing serious, or there was nothing unique about them, because they could even change if the ice was impure or if the water was impure. So this one is a better scale in that one of its fixed points, the absolute zero, has a greater significance than either of the centigrade fixed points. It is not possible to have a temperature lower than zero according to experiments. And sometimes it suggests that at 0 Kelvin, matter has no energy left in it, but this is not strictly true. It is just that for any matter at absolute zero, it is impossible to remove any more energy from it. The reason is very simple. At 0 Kelvin, the energy of matter is minimum. In fact, the kinetic energy could be zero, but the potential energy is minimum. So we define absolute temperature. We normally define absolute zero temperature as the temperature at which all substances have minimum internal energy. That is, the kinetic energy of the molecules is zero and their potential energy is minimum. So at absolute zero, the kinetic energy of the molecules is zero and the potential energy is minimum. So in general, we say at absolute zero, or absolute zero temperature, is the temperature at which all substances have their minimum internal energy. Note that this has never been reached. Although we have come within a few millionths of a degree, we have never reached absolute zero. That's why we say it is the most likely possible, it's the most likely smallest temperature, but in practice, it has never been reached. So let's try to convert the centigrade scale into the Kelvin scale by just using a simple analogy. One, we need to establish the fixed points of the thermodynamic scale. We mentioned the first one, which is the absolute zero, which is defined as 0 Kelvin. Absolute zero is 0 Kelvin, so that is considered to be the lower fixed point, or the lowest fixed point. On a constant volume scale, this is equivalent to negative 273.15 degrees Celsius, as we have already seen. So 0 Kelvin is equivalent to 0 Kelvin is equal to negative 273.15 degrees Celsius, which means 1 degree Celsius is most likely going to be positive, or which means 0 degrees Celsius is most likely going to be positive 273.15 degrees 15 Kelvin, as we shall see later on. Number 2, we also have the triple point of water. So these are the two fixed points on the centigrade scale, on the Kelvin scale. The fixed point of water is considered to be the temperature at which ice, that is solid water, then water, which is liquid water, and water vapor can coexist in equilibrium at the same temperature. Imagine water existing as a solid, a liquid, and vapor at the same time. That's what we call the triple point of water. Three states coexisting in equilibrium at the same time. And this one is defined to be 273.16 Kelvin by international agreements. That is about 0.01 degrees Celsius. This is called the upper fixed point of the thermodynamic scale, or the Kelvin scale. So on the Kelvin scale, the upper fixed point is 0.01 degrees Celsius, which is 273.16 Kelvin. So the triple point is found to be less dependent also on environmental conditions such as pressure than the ice point. Therefore, it is also very, very important and more significant. It is less dependent on environmental conditions such as pressure than the ice point. Of course, the ice point can be affected by pressure and impurities in the ice. So a gap between the absolute zero, that is 0 Kelvin, and the triple point of water, that is 273.16 Kelvin, can be divided into 273.16 divisions, such that each division is 1 Kelvin. The same way we divided the gap between 0 degrees Celsius and 100 degrees Celsius into 100 equal divisions. So even here, the gap between 0 Kelvin and the triple point of water, which is 273.16 Kelvin, can be divided into 273.16 Kelvin, 0.16 equal divisions to come up with what we call the Kelvin scale. Now, this arrangement is very interesting, that it makes a division on the Kelvin scale the same size as a division on the centigrade scale, which makes converting very easy and simpler. And it will make a change in the temperature on the degree Celsius scale to be equal to a change in the temperature on the Kelvin scale, as we are going to see. So using these two fixed points, the absolute zero and the triple point of water, can we therefore establish the Kelvin scale and come up with a simple formula that we can always use on the Kelvin scale. So using the constant volume gas thermometer, where we are going to assume that the gas used in here is an ideal gas, where the temperature varies perfectly linear with the pressure, or the pressure varies perfectly linear with the temperature. The two fixed points we are going to consider are: 1, the triple point of water, where on the degree Celsius scale it is around 0.01 degrees Celsius. 0.01 degrees Celsius, which is the same as 273.1 Kelvin. And this is going to be the triple point of water called PT. Then the other second point is this point here, where the pressure is 0, and this is called on the ice, this is called the absolute zero, which is going to be 0 Kelvin. So negative 273 is 0 Kelvin. So we have 0 Kelvin here, and we have the triple point here. So I can still use the gradient to come up with an expression to establish an expression for determining the unknown temperature on the Kelvin scale. So let me just say maybe the unknown temperature is here. Let me just call this one T, the unknown temperature, and I would say the property is the pressure P of the unknown temperature. So if I know the property at the unknown temperature, I know the triple point of water, the property of the property at the triple point of water. Of course, I know that if it is pressure, the pressure is going to be 0 at 0 Kelvin. Then I can use that to come up with the expression for temperature. That is, using gradient, I'll say that P minus 0 divided by the temperature is T minus 0 Kelvin. here I considered a pressure at the unknown temperature minus pressure at 0 Kelvin, which is 0, should be equal to the pressure at the triple point minus the pressure at 0 Kelvin, which is 0, divided by the temperature, as we have the triple point, which is 0.01 degrees Celsius. But because I'm dealing with the Kelvin scale, this will be 273.16 Kelvin minus the other one. This was pressure at the pressure at the absolute zero, which was 0. This is 0 Kelvin. So when I cross multiply this and I make T the subject, I have that P over T is equal to PT divided by 273.16 Kelvin. So it means the temperature T is going to be equal to P over PT times 273.16. Even though most of the times this equation will not be used for calculation, so this would be the equation that I would use for determining the temperature on the Kelvin scale if I know the thermometric property. But remember, the temperature on the Kelvin scale does not, or is less dependent on the thermometric property, or does not depend on the thermometric substance which is used in the thermometer. Okay. So the pressure reading of a constant volume gas thermometer is 1.5 times 10 to the power 4 pascals at the triple point of water. When the bulb is placed in a certain liquid, the pressure is 4.28 times 10 to the power 3 pascals. Find the temperature of the liquid. So the temperature is going to be the property over the triple point times 273.16. So the property is 4.28 times 10 to the power of 3 at unknown temperature divided by the property at the triple point, which is 1.50 times 10 to the power of 4. Then we multiply this by 273.16, and this gives us 4.28 exponent 3 divided by 1.5 exponent 4, then times 273.16. So this will give us the temperature as 77 or 78 Kelvin. The pressure reading of a constant volume gas thermometer is 1.367 times 10 to the power of 3 pascals at the steam point. What is the pressure reading at the triple point of water? So the temperature equals to pressure at the unknown temperature over pressure at the triple point, then times 273.16 Kelvin. So we know that the unknown, the temperature T is the steam point, which is 100 degrees Celsius, which we change to Kelvin. So this becomes 100 plus 273. This is going to be the pressure reading of a constant volume gas thermometer is this at the steam point. So P is 1.367 times 10 to the power of 3. What is the pressure reading at the triple point of water? So this is going to be divided by pressure at the triple point, then times 273.16. So I just want to find pressure at the triple point. So I'll just multiply 1.367 exponent 3 times 273.16 divided by 100 plus 273. So this is giving us a 1001.1 pascals, or 1.0 times 10 to the power of 3 pascals. So the pressure there is going to be 1.0 times 10 to the power of 3 at the triple point. Okay, so a few things we need to note from what we have just discussed. Number one, the scale is defined in a way such that scale divisions on the thermodynamic scale are equal in size to divisions on the centigrade scale, which makes conversions between the two scales relatively easy. Number two, a change in temperature of 1 Kelvin is equal to a change in temperature of 1 degree Celsius. So when you're finding difference in temperature, you don't need to convert after subtraction to get the difference. So because a change in temperature of 1 Kelvin is equal to a change in temperature of 1 degree Celsius. That's very, very important. And number three, I also want you to note that the units of temperature on the Kelvin scale is just Kelvin. It's not degrees Kelvin. So it's wrong to say degrees Kelvin. It's just Kelvin. Number four, on this scale, when we talk about ice point, it is 273.15 Kelvin. In other words, 0 degrees Celsius is the same as 273.15 Kelvin. And if we talk about the steam point, that is 100 degrees Celsius is the same as 373.15 Kelvin. Because remember we saw that 0 Kelvin was equal to negative 273.15 degrees Celsius, which means 0 degrees Celsius is equal to positive. Now it becomes positive 273.15 Kelvin. So it means 100 degrees Celsius is going to be 373.15 Kelvin. And lastly, ensure that all calculations are done using the Kelvin units for temperature in this unit, the same way we did in thermodynamics. I'll try to give an example for conversion, or you can even try to pause the video and try to solve this. So I will not solve 0 degrees Celsius. I will try solving 20 degrees Celsius to Kelvin. So 20 degrees Celsius is going to be equal to 20 plus 273, which gives us 293 in Kelvin. Because 20 was quoted as a whole number, I used 273 to convert it to Kelvin, and I wrote the answer as a whole number 293 Kelvin. I will give an example of minus 23 degrees Celsius. Minus 23 degrees Celsius is the same as minus 23 plus 273, which is going to be equal to 250 Kelvin. And because they gave us minus 23 degrees Celsius is a whole number, I use 273 to convert it to Kelvin, and I write a whole number. Let me try to check 45.21 degrees Celsius. If we are given 45.21 degrees Celsius, these are two decimal places, so I cannot use 273. So to convert this, I will say this is 45.21 plus 273.15 this side. I will use the actual value, that is two more significant figures, because this means this is more precise. So I will add this 45.21 plus 273.15. So this would give me 318.36 Kelvin. So for this precision, I will maintain the answer as 318.36 Kelvin. Mark the difference between this answer and the previous answers that I've just written. If we are to convert 34.4 degrees Celsius, then it means 34.4 degrees Celsius is going to be, because they have given us a decimal number, we are going to use 273.15. So this would be 34.4 degrees Celsius plus 273.15, which gives us 273.15 plus 34.4. This gives us 307.55 Kelvin. But because they quoted the answer to one decimal place, we shall round off this to 307.55 0.6 Kelvin, and this will be the most appropriate answer for this question. So here I was changing from degrees Celsius to Kelvin. On the other hand, from Kelvin to degrees Celsius, you just subtract. For example, 500 Kelvin is going to be the same as 500 minus 273, which gives us 227 degrees Celsius. Because they gave us whole numbers, you just write a whole number. If they had given us, for example, let's say 374.5 Kelvin. So 374.5 Kelvin would be the same as 374.5. This time I don't use 273, but I use a more precise value, which is 273.15. And this gives me 374.5 minus 273.15. This gives me 101.35 degrees Celsius, but because they gave us one decimal place, so this will round off to 101.4 degrees Celsius, and this will be the most appropriate value or answer to that question. And so many others, you can try to check them, or you go through the solved past paper questions. In conclusion, the problem with the centigrade scale is that the measurement on this scale only depends on properties of the substance, and yet thermometric properties do not always follow the straight line relationship between the two fixed points as it is always assumed. The thermometric properties that we always consider may not always follow the straight line relationship between the two fixed points as it is always assumed for the centigrade scale. Number two, so this one means the centigrade scales could be inaccurate at all points apart from at the fixed points. If you wish to compare the temperature accurately between two different experiments, you cannot use the centigrade scale. That means another scale has to be used. The absolute scale would be the perfect scale. The absolute scale would be the perfect scale since it has an absolutely straight line relationship between temperature and the thermometric property. And that means it is less dependent on the thermometric substance or the thermometric property itself. Unfortunately, this absolute scale is not a real scale, it is just an ideal scale, or it is a theoretical scale. So the problem with this absolute scale is that it is ideal and it a theoretical scale. We don't have such a scale in real life. It is just theoretical. But scientists believe it was possible. If it was possible to have such a scale, it would be it would be the perfect scale for measurement of temperature, because it wouldn't depend on the behavior, it wouldn't depend on the thermometric substance used in the thermometer, it wouldn't depend on the thermometric property of that substance. Unfortunately, it doesn't exist. It is just a theoretical scale. Okay, I think that should mark the end of lesson 1, I think.